So in today's lesson, we're going to be talking about electric current. And so electric current is a topic that you should be familiar with from your grade 9 science class. However, we will be revisiting some of the ideas just to remind you of the key concepts and extending that further and quantifying some of the ideas related to current. So just as water flowing creates a current, electric charges flowing create an electric current. And so if we zoom in on a wire, a conductive wire, we can describe current essentially as if we were to take a cross-section of this wire, okay, so just a spot, a cross-sectional area of that wire, and we were to measure the rate of flow of electric charges, okay, symbolized here by the Q, through that cross-sectional area in a given amount of time, that is what we would describe as the electric current. So I see here in this animation that I can see electric charges moving through. In this case, it's an electron. And we know that electrons are negatively charged, but there's actually a value associated with the charge on an electron. And if I had that information, and in this animation I can see a 10-second time interval, I can quantify the current by looking at the number of charges passing through this particular cross-section in a given amount of time. And so that would give me my current. So in a qualitative way, we can compare a large current to a small current in terms of the number of charges that are passing through a cross-sectional area per unit time. So for example, this large current here that I see on the left, I can see that if I were to measure this cross-sectional area, far more charges would be passing through that point in the same amount of time in comparison to the diagram on the right, where I see far fewer charges. And so we're going to use that idea of current being the number of charges passing through a particular point in a given unit of time to calculate it. So I want to remind you from grade 9 that I refers to the current, and the unit that we use for current is the ampere or amps, and symbolized by the capital letter A. So there's a difference between the symbol in the formula, which is the I, and the symbol used for the unit, which is A for amperes. Now, I said that was, essentially current was the charges per unit time. And so that is demonstrated through this formula, right? I'm taking the charge, Q, and dividing it by the time interval. So let's take a look at our units used for charge. So Q for charge is measured in a new unit called the coulomb. And the coulomb has the symbol capital C. And I'm going to take that and divide it by the time interval. And we're going to use SI units for time here, and those are measured in seconds. So I want to do a quick unit analysis here. So let's take a look at this. So I know that my current is measured in amperes. So I'm just going to put this in. Here's amperes. And so I know that Q here is measured in coulombs, and my time is measured in seconds. So I can say, therefore, that 1 ampere is equal to 1 coulomb per second. And that may come in handy just to look at what some equivalent or derived units are. So here's our first example. I'd like you to give this a try on your own to see how you make out with it. It's just an introductory question to get you utilizing some of these new units and a new formula. So calculate the current in an electric toaster if it takes 9.0 times 10 to the power of 2 coulombs of charge to toast 2 slices of bread in 2 minutes. So pause the video now, give the question a try, and then come back to verify your answer. Okay, so I've written out a solution here to the problem. I know that my charge Q is 900 coulombs. My time is 2 minutes, but I need to remember to convert that into seconds. So of course 60 seconds per minute gives me 120 seconds. So when I substitute that into my formula where current is equal to the charge divided by the time interval, and that gives me 7.5 coulombs per second, which of course I know is an ampere. Hopefully you did okay with that. Let's move on and carry on our lesson. So a scientist by the name of Milliken did this famous oil drop experiment, and he took a small oil drop and he suspended it between two parallel oppositely charged plates, and that allowed him to figure out what the charge is on an electron. So electrons and protons may have opposite sort of electric charge in terms of positive versus negative, but they have the same value in terms of coulombs. And so we can use what we know about charge overall and the number of electrons in a substance to relate that to the electric charge on a single electron, or vice versa. So, and this is a really useful formula if I happen to know the number of electrons that might be present in a particular situation, passing through a particular point in a wire, for instance, and I know the charge on an electron, I can know what the overall charge is for that circumstance, and that can allow me to get current as well. So this is the value, 1.60 times 10 to the negative 19 coulombs is the charge on an electron or a proton. Of course, the sign of that charge would be different for each of them, but you need to remember this value. We're going to be utilizing it in some of the problems that we solve in this unit. Okay, so here's a second example, a little bit more complicated than the first example that we saw. So we have a Goldleaf electroscope. I don't know if you remember those doohickeys from grade 9. It sort of looks like this. You have like a box often, or sometimes just like an Erlenmeyer flask, and you'll have like the little ball at the top here, and then a little bar goes down, and then you have these two little gold leaves. And so if you were to go ahead and touch the metal sphere with a charged rod, for instance, so here's like my charged rod, then what you may see is these little leaves spread apart, and that kind of indicates to you charges. So in this case, I have a Goldleaf electroscope with 1.25 times 10 to the power of 10 excessive positive charges. So this is telling me essentially the number of protons rather, that are present. Okay, and then I'm going to ground that. Remember, grounding just means touching and then allowing the excess charges to travel through you. And then it gets discharged in half a second here. Calculate the average current in the grounding wire. All right, so let's start to write out some of the details that we know here. And then what I'm going to do, once we've written out some of our givens, I want to give you the opportunity to try and work through this. So I'm going to ask you to pause the video, give the question a try, and then come back to it if you're stuck. So let's write out some givens. So I know that the number of charges is symbolized by capital N. And so in this case, I have 1.25 times 10 to the power of 10 charges, right? They happen to be positive charges, but that's not really relevant at this point. Now the fact that they're charges in general, they're positive charges, I know that they're protons. So, you know, that's just the number of charges, electric charges that are moving through. And so I can definitely use the fact that I know the charge on an electron, which was the 1.6 times 10 to the negative 19 coulombs. So I'm going to keep that in my back pocket. It's not said explicitly in here, but I do need to know it. Now, what else do I know? I know time. I know my time interval. And so in this question, what am I asked for? I'm asked for current. So pause the video now. I want you to give this question a try. See if you know how to solve this question. And if you're stuck, come back in a minute and check my solution out. Okay, so I want to take you through my thought process in solving this. I know that in this question I'm asked to find out the current in this situation, and the only formula that I know at this point that has current in it is this guy up here, so current is equal to the charge divided by the time interval. So I'm good with respect to the time interval. The question gives me that outright. But the problem is that at this point I don't have Q. And so what I need to do is I need to go ahead and find Q. And so what I thought about next was, well, what other formula do I know that has Q in it? And it's Q equals NE, where N is the number of electrons, and E is the charge on, or sorry, the number of particles, charged particles, times E, the charge per particle, whether it's a proton or an electron. And so that allowed me to first find out then my Q in coulombs. So I ended up with 2.0 times 10 to the negative 19. So at this point, I'm running out of space a little bit. So I'm going to actually just gear up over here and go ahead and finish this off. So I know that my Q now is 2 times 10 to the negative 9 coulombs. And I'm going to divide that by my time interval, which was half a second. And so this 2 is really 2.0. So dividing by a half is the same as multiplying by 2, so I can tell right off that that should give me 4.0 times 10 to the negative 9. And what unit am I using? Well, current is measured in amperes, so make sure you get that unit right. So before I set you up with a few homework questions to get you practicing some of this, I want to just make a quick mention of the difference between conventional current and electron flow. So early on, scientists weren't really aware of the charge on electron. They really didn't have any knowledge of that, and so they assigned the movement of the current in terms of moving from positive to negative terminal in a battery or a cell. And so what we call conventional current, it really describes not really so much the flow of electron, but just the motion of the current from the positive to the negative terminal. Now we now know that, the electron is negatively charged, and so in the battery, the electrons are going to move from negative to positive. And so when we talk about electron flow, we're talking about those electrons moving from the negative terminal to the positive. So conventional current, we describe the current moving from positive to negative. If we describe electron flow, we're looking at it moving from the negative terminal where it's sourced to the positive terminal, which it's going to be attracted to. So just a special note, if you see the arrows that seem to be pointing in the opposite direction to what you would expect, it's likely because the circuit is drawn in terms of the conventional current model. So to finish off, here are some questions that I would like for you to work on in relation to electric current, just to get you internalizing some of these ideas and able to use the formulas that we learned today effectively. Please see me if you have any questions or concerns.